What I would like to do in this presentation is to describe what is isoelectronic species. It is one common trend that we typically investigate in periodic table. Electronic. Iso means same. Electronic, electron. So obviously, isoelectronic species is a group of atoms or ions that has same number of electrons and they have same electronic configuration. I'm going to use element from period 3 and 2 as example of isoelectronic species. Okay, so for period 3 is sodium ion, magnesium 2 plus ion, aluminum 3 plus ion, and element from period 2 is nitride, oxide, and fluoride. All of these ions have 10 electrons and they all have the same electronic configuration as neon. These ions form after they lost or gain electron in order to achieve stability of octet configuration. So the benchmark for you to identify ions as isoelectronic species is they will have some same number of electrons and same electronic configuration. So in this case, all of these ions have the same electronic configuration 1s2, 2s2, 2p6. Now let's discuss the size of isoelectronic species. Within isoelectronic series, the more positive the charge, the smaller the species. So now we look at the trend of element ion from period 3. We have sodium plus, magnesium 2 plus, and till aluminum 3 plus. If we look at the charge, the number of charge for sodium plus is +1, magnesium is 2 plus, aluminum has 3 plus, and the positive charge is actually increasing. But if you look at the ionic radii, which is from sodium to aluminum, the number is decreasing, 95 to 50 picometer. So the more positive the charge, the smaller the species. Okay, now let's look at the anions for isoelectronic species. The negative charge, the trend in negative charge ions. The more the negative charge, the larger the species. So from fluoride to oxide until nitride. So fluoride has -1, oxide 2 minus, and nitride has 3 minus charge. So as the negative charge is increasing, okay, the more the negative charge, we can see that the ionic radii of fluoride to nitride is increased from 136 to 171. So what I can conclude here is from the more positive to most negative ion, the size of isoelectronic species is increasing. Here we are going to discuss the reason of why there is difference ionic radii in isoelectronic species. What we can look at here is the number of proton in the nucleus influence the electrons surrounding the nucleus, and there's gonna be attraction between the nucleus. So the more protons in the nucleus, the greater the attraction, the smaller the ionic radii. From figure below, figure 2, you can see the smallest ion is actually aluminum 2+, and it has highest number of protons. Okay, so it has highest the number of protons among these elements. The largest would be nitrite, okay, which only has 7 numbers of protons. Okay, so if you look at when the higher the number of protons, the higher the value of effective nuclear charge. Okay, so that's the reason. So if you look at some elements arranged, you first have to figure out how many protons they have, how many electrons they have. If they have same numbers of electrons, so it is isoelectronic species, and the smallest ion will be the one with the most number of protons with highest effective nuclear charge. Now let's discuss exercise 1. This exercise needs you to choose which particle is larger. So it is a comparison of size between ion and its neutral atom. So the first species we are going to compare is aluminium and aluminium 3+. First thing you have to know is the number of proton for both aluminium for both particle. So for this particle has same proton number, okay, which is 13, and aluminium is a neutral atom. So for neutral atom, it will have same number of electron, which is 13. Okay, so for aluminium 3+, I know you already know that for the formation of aluminium 3+, we know that aluminium loses 3 of its valence electron. Then the remaining electron in aluminium 3+ is 10. So for aluminium 3+, it has less number of electron if we compare to the aluminium atom, but the number of proton is still the same. So the attractive forces felt by the remaining electron is stronger. Now all the electron cloud will come closer towards the nucleus, and the electron cloud shrink. So the aluminium 3+ will have smaller size. Okay, so for this question, they ask you to choose the larger particle. So the larger particle will be aluminium. So that is the answer. So the next one, we are going to compare between sulfur and sulfide. So this is a comparison of atom and anion. So the first thing, as I said before, the first thing you have to identify is the number of proton. Okay, so proton number for sulfur is 16 and sulfide also. And the number of electron for sulfur is 16 since it's neutral atom. So to form sulfide ion, sulfur has to gain 2 electron. Here, 2 minus. This means that sulfur has gained 2 electron. So we can see that the number of electron for sulfide now is 18. So it has more number of electron compared to sulfur atom. So since sulfide has more number of electron than its neutral atom, there is exists of mutual repulsion between the electron. Okay, so the mutual repulsion is increased. So when there is more repulsion, the electron cloud will spread out. So the size of sulfide is larger than its neutral atom. So the answer for number 1B, question exercise 1B, is sulfide. Here, so here answer. So for exercise 2, we are going to write the electronic configuration for given ions, and you have to indicate which are isoelectronic species. So as you already learned before, isoelectronic species is the species that have same number of electron and same electronic configuration. Okay, so to solve this question, since the question gives you ions, you need to identify the number of proton first for each species from its the neutral atom. So for calcium, okay, so for calcium atom, it has 20 number of proton, and for oxygen it has 8 number of proton, and for potassium it has 19 number of proton. So for neutral atom, we know that the number of electron would be the same. Okay, so the number of electron for calcium is 20. The number of electron for oxygen is 8, and the number of electron for potassium is 19. So from the number of electron you identify from the neutral atom, now you can write the electronic configuration of atom first. Okay, you cannot directly write the electronic configuration of ions. Okay, so let's discuss the answer. Just write the electronic configuration for calcium atom first, which is you will get 1s2, 2s2, 2p6, 3s2, 3p6 for s2. And to form calcium 2 plus ion, it needs to lose 2 of its valence electron here, okay, which is from 4s2 for s orbital. And now the configuration will become 1s2, 2s2, 2p6, 3s2, 3p6. And now it has achieved stable octet configuration. Okay. For oxygen, you will see that the configuration will become 1s2, 2s2, 2p4, since it has 8 number of electron. To form O2 minus oxide ion, it has gained 2 electron. Now the 2 electron will come to 2p orbital, so it becomes 2p6. So the configuration for oxide is 1s2, 2s2, 2p6. Okay, and the last one is for potassium. For potassium, it has 19 electrons, so the configuration will become 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So to form potassium plus 1 ion, so it needs to lose 1 electron. So the electron, you have to remove the electron from the outermost shell, which is 4s1. Okay, and the configuration will become 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so if you look at the ion here, you compare these 3 ions. So for calcium and calcium 2 plus and potassium plus 1 has the same electronic configuration and same number of electron. So the answer is calcium 2 plus and potassium plus are isoelectronic species. Are you familiar with this symbol? So this is X-ray radiation symbol, so we can see a lot of this symbol at this hospital. So, and I'm sure some of you have experienced X-ray test, right, at the hospital, which is this test, X-ray test, is actually a quick, painless test that produces image of the structure inside your body, particularly your bones. So instead we use for X-ray radiation in chemistry. X-ray radiation also can be used as energy source for ionization process. So the next lesson we are going to study more about ionization energy. Ionization energy is one of the important atomic properties. In an atom, the electrons are attracted attracted by the positively charged protons. That is, there exists an electrostatic forces of attraction. So there are attraction between the nucleus, the protons in the nucleus, and also the electron. So to remove the electron, of course, we need energy. Okay, so there are two specific definitions that you are going to learn. The first one is first ionization energy. First IE means that the energy required to remove the first electron. The first electron you are going to remove is from the atom. Okay, so this is the definition. It is the minimum energy required to remove an electron from gaseous atom in its ground state. Now let's take a look at the process by using an equation here. So if you have a magnesium atom, your magnesium atom should be in the gaseous phase. Okay, when you remove the first electron, okay, so it becomes magnesium ion, magnesium plus 1, but the phase is still in the gaseous form. Okay, delta H here is actually represent the ionization energy. Okay, so to remove the first electron, so for example, this is your first electron of magnesium. Okay, I'm using this picture. Okay, so this is magnesium atom. So when you remove the first electron, this is the amount energy needed. Okay, the minimum energy. So if you have 736 kilojoule per mole, then you can remove the first electron. So this is what it means by minimum energy. If you have more than 736, of course, you can still remove the first electron. Now let's take a look at the second ionization energy. Further by applying more energy, we can also remove the second electron from the atom. Okay, but you have to supply more energy. The energy required here is, we call the second ionization energy. So it can be represented as shown in the slide. Okay, to remove from the definition, the second IE is the minimum energy required to remove an electron from positive gaseous ion in its ground state. So the process can be represented in equation below, which is magnesium plus gas. Okay, this species already formed after you come from the first IE. After you remove the first electron, you are going to remove the second electron from the ion. Okay, not from the neutral atom. Neutral atom is only for the first IE. Okay, so this is the second electron you are going to remove. Okay, then you will form the magnesium 2 plus gas. Okay, so I hope you don't have a misconception. We are not remove. Sometimes students write this equation. They put 2 electrons for the second IE. Okay, you have to remove the second electron, only an electron, from a gaseous ion to form magnesium 2 plus. The charge is already on positive 1 here. So if you remove the second electrons, and it becomes 2 electrons. So you don't have to put 2 here. Okay. So delta H, I mean the second ionization energy required to remove the second electron is 1450 kilojoule per mole. Second IE is always higher than the first IE. This is because it always takes more energy to remove an electron from the positive charge ion than the neutral atom. Okay, we need more energy. Why? Because you have already learned about this in periodic table. When the first electron is removed from the atom, we have the ions still have the same strength of self. Okay, because it has same number of protons. So the attraction of the nucleus and the remaining electron in ion is getting stronger. So it's quite difficult to remove the next electron. So when you are going to remove the second electron from the ion, you need more energy. Okay, So that's why second IE is always higher than the first IE. Now let's look at the animation on how the first ionization process takes place. When energy such as photon or X-ray is applied, and that energy will pass through the gaseous atoms, the electron in outermost shell will be pulled out due to the electrostatic forces. So from the neutral atom, and it will form the ions. There are three factors affecting the ionization energy. The first one is atomic radius. As the atomic radius increases, it said the ionization energy decreases. So it's easier to understand if you can imagine, if you have a larger atom, okay, if you have a larger atom, the forces attraction between the nucleus and the valence electron is weaker, because the valence electron is quite far away from the nucleus. So it's easier for us to pull out the electron, so we don't need high energy to do that. So that's why the larger the atomic radius, ionization energy decreases. Okay, the second one is effective nuclear charge. Zaf said that here effective nuclear charge increases, the attraction between the valence electron and the nucleus becomes stronger, so ionization energy increase. So this factor we use to explain when we have element across a period. So across a period, ionization increase. This is expected as a force of attraction between the electrons becomes stronger across a period. Okay, so the increase in sum of attraction can be explained by increase in number of proton across a periodic table. So when across a periodic table, we know that the proton number increase. So of course, effective nuclear charge is independent on the number of proton. So effective nuclear charge also increase. So the attraction between the valence electron and the nucleus becomes stronger. And of course, when the attraction is strong between the nucleus and electron, it's quite difficult to remove the electron. So we need more energy. So the ionization energy increases. Okay, so but the trend is reversed from the fact that the principal quantum number become larger down a group. Okay, this led to the third factor, which is shielding effect. So even though the number of proton increase in the nucleus as we go down a group, it is still easier to pull out the outermost electron from the last element in the group. Okay, and the last element of the group. This is due to the presence of the higher number of inertia of electron. We have high number of electron, which is effectively shield the outermost electron from the nuclear forces. Okay, so ionization energy decrease down a group.